So in this video, we're going to learn about horizontal projectiles. So let's say I were to have a cliff, and off the top of the cliff, I were to launch, let's just say a cannonball or something to the right, perfectly horizontally, and let's say it's going at 20 meters per second. That projectile would fly through the air, right, horizontally, and then it would start to fall towards the ground and strike the ground over here. And again, this really isn't a good motion diagram. I'm just trying to show the path of the projectile, right? Now, there's some things that we could figure out about this. We could figure out, well, what is the displacement, and specifically the down displacement, which I'll call dy, or d in the y direction, right? We also could figure out how far from the base of the cliff the object threw. So this is another d, but in this case we would call it dx, or in the x direction, right? We also could figure out time, how long that projectile was flying through the air. So we need to start thinking about this vector as a two-dimensional vector that has components, right? So as the object flies in this direction, if we ignore air resistance, then the velocity in the x direction should remain constant, right? There's nothing causing it to accelerate in the x direction. So here it would be 20 meters per second, and I'll try and draw them about the same size. Here it would be 20 meters per second. Here it would be 20 meters per second. Here it would be 20 meters per second. And right before it strikes the ground, it would be 20 meters per second. There's no force, and we'll learn in the next unit, that really forces are what are going to cause this object to slow down. So there's nothing causing an acceleration in the x direction, right? So let's write that down here. Velocity in the x direction remains constant. Now let's talk about the y component. At first, if the object is launched perfectly horizontally, the velocity at the y at the beginning would be equivalent to 0. Okay? And then as it flies through the air, it starts to fall down, right, because of gravity. So initially I have a velocity of 0, but then I start to get a larger and larger velocity vector. Right? So we can see that the velocity in the y direction is increasing. So let's write that down. So velocity y, this my purple pen is a little bit better, begins at 0 and then accelerates due to gravity. All right, now if we look at the time, let's think about the time aspect of things. So if we separate out our x and y components, we can think about them individually from one another. But there's one thing that's going to link the y motion of the object and the x motion of the object, and that is time. So as the object flies off, time passes and it strikes here. So the y motion and the x motion of the projectile have an equivalent time. So time for both the velocity in the x and velocity in the y is the same. All right, so time is really what's going to link our two sides of the problem. But what really determines how long something is in the air? Well, in this case, we know that gravity is what's bringing it down to the ground. So gravity, or little g, determines time. Right? So let's give our cliff a height. Let's say my cliff is 50 meters up in the air. Let's try and use this in order to figure out gravity and how gravity affects the time that the object's in the air, all right? So we're going to say that d equals v initial t plus 1/2 at squared. I have to use a constant acceleration equation because in the y direction I see acceleration, right? So I know that my initial velocity in the y direction is going to cancel. And so I get d equals 1/2 at squared. Or I could do, -50 and -10 there. So let's just do this. 50 is equal to 1/2 of 10t squared. And if I wanted to make these negative, I could, but they just end up canceling out anyway. So I'm just going to do 50 divided by 5. So I get 10 is equal to t squared. So let's just take the square root of 10. And I get 3.16 seconds. So t is equal to 3.16 seconds. Now notice, this is the same exact equation we would have used as if I would have just dropped the ball, not even launched it horizontally. So it takes the same amount of time to drop an object from some height as it is to shoot it horizontally. So if I were to shoot this cannonball and drop another cannonball at the same time, right, they would both strike the ground 3.16 seconds later. All right, so now that I have the time and I know the time that the object is flying through the air, now I can start looking at my x components of the problem, right? So let's try and figure out how far this object has gone. So if it takes 3.16 seconds as it's traveling in this direction, how far in the x direction from the base of the cliff does it land? Well, it's important to remember that the velocity for the x component is constant. So I don't need to use an acceleration equation. I can just use very simply that velocity in the x direction is equal to distance or displacement in the x direction times time, right? So in the horizontal direction, I do not need to take into consideration any acceleration. So just easily I can take velocity, which is 20, and multiply it by 3.16, and that gives me 63.2 meters. All right, so this pretty much defines all of the things that you need to know in order to solve for horizontal projectile problems. One, that the velocity in the x direction remains constant, and so I can use velocity equals distance over time. Two, the velocity in the y direction begins at 0 and then accelerates due to time, or due to gravity, excuse me. Time is dependent on gravity, and it is equivalent for both the x and the y direction. All right, so that's all you should need to know to solve any horizontal projectile problem.